next speaker is Brandi Henry from Eastern University. She's been working under the direction of my departmental colleague Bob Hartman this summer, and she'll be discussing star spots on LO Pegasi 2006 through 2015.
I just want to apologize for my voice too ahead of time. I think I screamed a little too much at King Silent the other day, so bear with me as I try to get my words across. Alright, so like Dr. H.K. said, my name is Brandi Henry and I worked with Dr. Hartman this summer, and I will be presenting on star spots on LO Pegasi. So let's first talk about a star that we know very well, our own sun. So stars form from the collapse of interstellar gas. And as that gas is collapsing, you're getting really high temperatures in the core, reaching up to 15 million Kelvin in the sun. These high temperatures allow the hydrogen ions to collide and fuse to form helium. In that fusion process, energy is released and it's carried out through the radiation zone by photons. At the surface of the sun, then you have the convection zone, where hot gas is rising, it will cool, and then sink back down. And on the surface of the sun, we have darker, cooler spots called sunspots, and that's what we're interested in. So George Elliott Hale first discovered that sunspots are caused by magnetic fields using the Zeeman effect, which says that if you have an atom with all of its electrons in the degenerate state, and you put it in a magnetic field, the degeneracy of the electrons split, and they enter different energy levels. And that split is observable in the spectral lines. So here we have the spectral line of a star spot, and we see that it goes from one spectral line to 3 there. So Horace Babcock came up with a model of how the magnetic field lines on the sun behave. So first we have the colloidal field lines with the magnetic field lines running from pole to pole. And then we see the sun start to differentially rotate. So that just means that the plasma around the equator of the sun is rotating faster than the plasma at the poles of the sun. And as it does that, it drags the magnetic field lines with it. And it's able to do that due to a thing called flux freezing. So Faraday's law says that the electromotive force is equal to the negative time derivative of the flux of the magnetic field B. And Ohm's law says that same electromotive force is equal to the current through the resistor times the resistance of the resistor. So for a perfect conductor, we want R to be 0. Well then, according to Ohm's law, the electromotive force is also 0, which according to Faraday's law means that the change in the flux field over time is 0, so then the flux is constant. So that's what's happening in the superconducting loop. So in a superconducting loop, if you have magnetic field lines running through it, they become frozen in that loop. And if that loop moves, it drags the magnetic field lines with it. And that's what we see happening here. So it turns out the sun's plasma is actually a very good electrical conductor with all of its ionized atoms and its free-floating electrons. And so then we find that the magnetic field lines become frozen in that plasma and move with the plasma as it begins to differentially rotate. And we end up with the magnetic field lines getting wound around the sun, and that's called toroidal field lines. So these magnetic field lines bundle in flux tubes in the plasma, and these flux tubes must be in pressure equilibrium. So outside the tube, we have the pressure of the gas. Inside the tube, we have the pressure of the gas as well as the magnetic pressure. And we end up with this relationship then, from which we can infer that the pressure of the gas outside the tube is greater than the pressure of the gas inside the tube. From the ideal gas law, we know that the pressure is equal to the density of the gas times the Boltzmann constant times the temperature over the mean molecular weight times the mass of the hydrogen atom. So we substitute that into our relationship between the gas inside and outside of the tube, and if the temperatures inside the tube and outside the tube are the same, we end up with the density of gas outside of the tube being greater than the density of gas inside the tube. So when you have something less dense and something more dense, it rises up and it floats. And so we have the tubes are buoyant and they pop out of the plasma of the sun. So a really good way to think about this is if you have a pool noodle and you submerge it in the water and move your hand to the end of the pool noodle, the middle of the pool noodle will rise up out of the water and pop out. And so that's what's happening with the flux tubes in the plasma of the sun. And they're made of magnetic field lines, so they're called magnetic loops. And these are some pictures of magnetic loops on the sun. And this is where we have that happening in Babcock's model. So these emerging magnetic loops are composed of magnetic fields, and they are bursting through the plasma of the sun, and they're interrupting that convection zone. So if the magnetic field is weak, convection is going to carry on as normal. But if that magnetic field is strong, we're going to have very rigid magnetic field lines, which is going to suppress the side-to-side motion of convection. And so that spot then must rely on radiation to emit heat instead, which is much less efficient. So we end up with darker, cooler spots where strong magnetic field lines are bursting through the plasma of the sun. And as that happens wherever the strong ones are bursting through the plasma of the sun, we're going to have one where it exits the plasma, and then also one where it re-enters the plasma. And so we have sunspots coming in pairs most times. Okay, so here's Babcock's model. So let's say that this is the north magnetic pole and this is the south magnetic pole. We have the pole magnetic field lines getting twisted around the sun due to the differential rotation and flux freezing. We eventually get our magnetic loops and our sunspot pairs, and eventually we have the reversion of the magnetic poles with the south in the top and the north in the bottom. We're not entirely sure how this happens. It's not just a surface level phenomenon, it's much more complex than that, but we do know that it takes the sun 11 years to go through this process. Then it takes another 11 years for it to get from here back to here, and that is known as the solar cycle, and then takes 22 years. So what about Alopegasi? I've been talking about the sun the whole time. Well, sunspots and star spots are the same thing, just star spots in the sun are called sunspots. Alopegasi also has a similar structure to the sun, and it takes 10.15 hours for Alopegasi to rotate once. Its star spot cycle is about 1 year, so what the sun is doing in 22 years, Alopegasi is doing in 1 year. So that means that its light curve is changing significantly over that course of 1 year. Alopegasi also is ideal to study because it's visible in the nighttime sky from our observatory from May to November. So how do we go about doing this? Well, as you can imagine, if you have a star with no spots, it's going to appear a lot brighter to us here in Ohio than a star with spots on it. The same sort of logic can be applied to a single star that is rotating. So as the star is rotating, if we have the star spot coming into view, it's going to appear a lot dimmer to us here on Earth than when the spot rotates out of view. And so here we have a plot of intensity or brightness versus time, and we can see how it's changing relative to the rotation of the star. So our first step is to measure how the brightness of the star is changing over time, and that's going to be able to tell us when the star spots are rotating into view and out of view, and also where they are located on the star. So Dr. Harmon came up with a computational method to develop three-dimensional surface maps of Alopegasi. So we feed the program a light curve which plots its magnitude or brightness versus rotational phase, which just says where the star is in its rotation. And it also takes an Li disco ball, which is actually a sphere of radius 1 with n latitude bands that are divided up into squares of approximately equal area. The program then applies spots to the disco ball so that as it rotates, it matches that light curve and the change in the brightness as it rotates. So here we have a bit of a game changer then. So Alopegasi has an angle of inclination of approximately 45 degrees towards Earth. So here you can see its rotational axis and the angle at which it's tilted towards Earth. Please note this is not to scale. So that means that one of the poles of Alopegasi is always facing Earth. So let's say that there's a spot on that pole. Now, if Alopegasi is rotating, that spot is always going to be in view to us. And so it will never rotate into or out of view. And so though as we're measuring the change in brightness, we'll notice it doesn't change, even though there is a spot there. We aren't aware of that spot because the brightness is not changing over time because the pole spot is always in view. So our measurements of the change of brightness are not sensitive to the presence of pole spots. So what do we do about that? Well, this summer we've been working on coming up with the pole spot sizes for Alopegasi over the past years. We've come up with 2 different methods to do that. So method 1, we know that 2010 is the brightest year. We then say, let's assume that the brightest year has no pole spots. And when we make our Li inversions, we can get a couple different surface maps from one light curve. And the way it does that is it gives us 2 spots, or it gives us spots with different sizes. And so now these 2 stars have the same brightness dictated by that original light curve it was fed. So how does that work if they have 2 different size spots? Well, the brightness of the star is dictated by this photosphere. And the photosphere in these stars are the white squares. And so this star, as you can see, has much less white squares than this top star. So the white squares in this star must be a lot brighter and emitting a lot more light in order for them to have the same brightness. So that means that this star has a greater average photospheric intensity, or a greater average brightness for those squares. So what we can do is have 2010 with no spots, we can find its average photospheric intensity. We know that the photospheric intensity should not be changing. And so then we can take that and match all of the photospheric intensities to the other years through the surface maps that were given to us by the program, and we can determine then the spots of the size of the pole spot for those years. And method 2, we would utilize Doppler imaging and the accompanying light curve for that year. So Doppler imaging is going to tell us the size of the pole spot. We then take the light curve, we invert it, we come up with our surface maps, and then again, we use the Doppler imaging to determine what size the pole spot should be. Again, we then find the photospheric intensity for that year, and we go through the process of matching the photospheric intensity to other years again. So we have employed method 1 so far, and this is 2010, the brightest year, so as you can see, it does not have a pole spot. And this is giving us the change in the pole spot sizes throughout the years, as well as the star spots that are on Alopegasi. It's not likely that 2010 doesn't have any pole spots, but this will at least give us the smallest pole spot sizes for the years, and it also shows us the relative change in the pole spot sizes. Please note that these are also just the B filter inversions for the pole spot sizes too. We use B, I, R, and B for the different filters. We hope to, in the future, be employing method 2 when we can get some Doppler imaging and accompanying light curves. So I just want to say thank you guys for listening. Also, special thanks to the NSF Foundation, the RU program there, to Ohio Wesleyan University, and to Dr. Harmon for this summer research experience.
Okay, thank you, Brandi. Questions?
So you guys haven't actually used method 2, right?
No, we still
Okay.
have to work at getting Doppler imaging and the light curves for that. So,
And do you expect like the results to be more accurately with method 1 or not?
yeah, it's not likely that 2010 doesn't have any pole spot, so it's likely that it does have a pole spot, which is going to change the average photospheric intensity. So then we will be able to get a better idea of what all the pole spot sizes are for other years, but those are at least going to be minimum pole spot sizes. So it kind of gives us a relative change idea and the minimum that it could possibly be.
So do you expect the second method will give you like the absolute size of the pole spot or the relative size?
I think it will give us a more accurate size of the pole spot. I'm hesitant to say the perfect or exact, just because there always seems to be error in science, but we're humans, so we'll allow a little bit of error, we won't go with exact. But yeah, it should be a lot more accurate than that, yeah, and it won't be just relative.
Brandi, you mentioned a few filters that were used at the end. Can you help remind me of what they do, just briefly?
Yeah, so we use the B, I, R, and V, which is the blue, the infrared, the red, and the visible filters. And those are just filters that we use. So as we are looking at the star and taking our images with that, it's only letting certain wavelengths of certain size through, so that we can look at that.
All right, let's thank you.